Good morning, dear students. Today we will be discussing hyperbola, that is in continuation of whatever we have discussed in the last couple of classes. And today we will start from a directed circle of hyperbola. If you recall that we discussed earlier when we discussed in ellipse, that directed circle of ellipse. So in context to that, what is directed circle, of hyperbola? So the directed circle of a hyperbola is the locus of the point of intersection of any two mutually perpendicular tangents to the hyperbola. That means what? That you know you take a hyperbola, and then you find that two mutually perpendicular tangents to the hyperbola. Okay, mutually perpendicular hyperbola. Then their point of intersection, you find a locus, and that locus is known as the directed circle. Okay, so as it is similar to ellipse, and ellipse I explained in details about the directed circle. So it is in the similar line for hyperbola as well. So I'm just making this information, and we'll discuss about the equation of the directed circle. So dear students, as you see, the definition what I wrote here is that the directed circle of a hyperbola is the locus of the point of intersection of any two mutually perpendicular tangents to the hyperbola. Okay, now there are some relevant points with respect to directed circle, but before that we should know what is the equation of the directed circle of the standard equation of a hyperbola, like x square by a square minus y square by b square equal to 1. So suppose that we have that hyperbola having standard equation x square by a square minus y square by b square equal to 1. Then the equation of the directed circle is actually x square by a square, x square plus y square is equal to a square minus b square. That is the equation of the directed circle. That means the directed circle having the center exactly like the center of the hyperbola, that is in this case it is the origin, and and the radius of the directed circle is square root of a square minus b square. Okay, dear students, so I hope you got it very clear about the directed circle. Okay, now I'm not drawing any diagram as long as the directed circle is concerned. As I said, it is exactly like ellipse, so you can follow it from there as well. So there are some important points, and those points related to directed circle, and I would like to discuss those points. The first point, dear students, is that the directed circle of a hyperbola exists if a is greater than equal to b. Obviously, if a is less than b, then you see that radius becomes square root of a square minus b square, which is square root of negative, means an imaginary number, which is not possible. So obviously the directed circle of a hyperbola exists if a is greater than equal to b. And the second point is that from any point on the directed circle, if any two tangents are drawn to the hyperbola, then the angle between the tangent must be 90 degrees. Absolutely. So this is another point. Okay, and that is actually coming from the definition of directed circle. And third point is that if a is less than b, then there exists no point from where two mutually perpendicular tangents can be drawn to the hyperbola. That actually coming from the first point, what I said is that the directed circle of a hyperbola exists if a is greater than equal to b. When a is less than b, that means when you do not have any directed circle, when you are not able to construct any directed circle of a hyperbola, that says that definitely it is not possible to find a point from where two mutually perpendicular tangents can be drawn to the hyperbola. Correct? So this is the third point as long as the directed circle of hyperbola is concerned. Now, dear students, I will move to the next point, that is called normal of hyperbola, and that I will discuss in the next page. And here it is. Never hesitate to ask me any question if you have, okay, any. So all of us are aware of what is normal. We have discussed several times in our previous, two-dimensional coordinate geometry discussions, like circle, then parabola, then ellipse. Okay, in the same line, it is also here in hyperbola. So still, I can tell you, normal is nothing but a straight line, which is perpendicular to the tangent. And at what point it is perpendicular? The point where the tangent is drawn to the to the curve. Okay, so for example, if I just give you a visual representation, suppose in case of a curve like this, suppose this is a curve, and in this curve you get a point here, that is a point P. Okay, and at that point P, you draw a tangent. Okay, first let's draw a tangent. Let me draw the tangent in the green color. So if this is the tangent to the curve, okay, at the point P on the curve, and then what is normal, dear students? Normal is nothing but a straight line which is perpendicular to the tangent. So that means a normal will be looks like this. Okay, where we can say is that this angle is 90 degree. This angle is 90 degree. Okay, so then the green line is known as a normal. Okay, so this is the fundamentals about normal. We have discussed several times, but here we are going to discuss in context to the hyperbola what are the equations of the normal. Okay, the first point is that we'll consider the standard equation of hyperbola, like x square by a square minus y square by b square equal to 1. That is the standard equation of the hyperbola. And in this standard equation, dear students, if you see that if we get a point P having a coordinate x1 comma y1, that is a Cartesian coordinate, then what is the equation of the normal? Equation of the normal is x minus x1 by x1 by a square equal to minus of y minus y1 by y1 by b square. That is the equation of the normal to the hyperbola x square by a square minus y square by b square equal to 1 at the point P having coordinate x1 comma y1. Now, if the point P is given as a parametric point, okay, then the equation of the normal to the hyperbola x square by a square minus y square by b square equal to 1 at that parametric point P, which is given as theta, that is actually its coordinate is a sec theta b tan theta, is actually ax cos theta minus by cot theta is equal to a square plus b square. So dear students, I will suggest you to remember these equations, so that when we solve the problems, you can directly apply this, and it will take much less time to solve. Now, if anyway you are not able to recall, for example, in worst case, then what you can do is that the equation of the tangent to the hyperbola, okay, and then you can use the point slope form of a straight line, that is y minus y1. If you recall, y minus y1 is equal to m into x minus x1. Now, from the equation of the tangent, what is the value of m. So the value of m for normal should be minus 1 by m, that is minus 1 by slope of the tangent. So that you can apply, and from here also you can find it out. Correct, dear students? So if you are not able to recall by any chance. So anyway, that was I just wanted to say you that, okay, how you can leverage the equation of the tangent to find the equation of the normal. So, dear students, now what I'm going to discuss is that the pair of tangents from an external point. Okay, and let me explain you this thing by means of a diagram first. After that, we'll go to the different equations, relevant equations, and I will discuss in the next page. So the point here is that the pair of tangents, from an external point. So let us first visualize this particular, situation, that what it is actually, how it, how we can visualize. So if you look into this one, so this is a point P, this that is a point. This is a point P with coordinate x1 comma y1, and this is the hyperbola. Okay, this is hyperbola, dear students. So from that external point P, you are able to draw two tangents. One is PA and the other one is PB. So what we are going to do is that we are going to find the equation of these two tangents PA and PB. Moreover, we are going to see that how we can jointly represent these two pair of tangents, and that becomes a pair of straight lines. That means it will be a equation in second degree in x and y. So let's see how we can find it out. Here we will take the similar approach, the way we have done it for parabola and ellipse as well. Okay, so here we will give the symbolic representation of few expressions, and from there we will be able to find it out, dear students. So here it is. If you see the equation, let me first place it here. Yeah. Okay. So the equation of the pair of tangents drawn from an external point P having coordinates x1, y1 to the hyperbola x square by a square minus y square by b square equal to 1 is s1 equal to t square. So dear students, s1 equal to t square is a symbolic representation. So what is s? S is nothing but x square by a square minus y square by b square minus 1. That is the expression S. Now what is S1? S1 is the expression S where you replace x by x1 and y by y1. And we get the value of S1 as x1 square by a square minus y1 square by b square minus 1. And what is t, dear students? T is nothing but the value of the expression x1 by a square minus y1 by b square minus 1. Now, here I would like to tell you is that if you look into that, the t equal to 0, if you make it as if it is like an equation of a tangent. But that context is, we are, we are just using that concept that as if P is on the point on the hyperbola, but practically it is not. As you see, the point P is outside of the it is not on the hyperbola. Okay, so so that we can draw two tangents. Okay, now the point is that from here what you see is that the expression T, that is x1 by a square minus y1 by t square minus 1. And if you equate it to 0, as if it is like the equation of a tangent to the hyperbola at the point P x1, y1. But that is not practical. But here we are just remembering from a symbolic representation point of view. So that if you recall, always you can recall is that ss1 is equal to t square. That is the equation of the pair of tangents from an external point having coordinates x1, y1 to the hyperbola x square by a square minus y square by b square equal to 1. Okay, so this is the equation of the pair of tangents. I hope things are clear to you. The next point what I'm going to discuss, dear students, that is called the chord of contact, and that I'm going to discuss with you. It is exactly the concept is similar to that of ellipse, and you can get those video lectures of ellipse in YouTube, as well as you can get it from the online test platform at KonarClasses.com. So in case you need to go back to look into it, what is meant by chord of contact, you can look into it. So well, let me first place the statement from the study material, and then let me explain you further. So let the pair of tangents drawn from an external point, let the pair of tangents drawn from an external point P x1, y1 to the hyperbola x square by a square minus y square by b square equal to 1 touches the hyperbola at two distinct points, say A and B. Okay. Now, um, now the straight line AB is called the chord of contact, and its equation is t equal to 0. Okay. So let me give a visual representation of this particular problem. So if you recall that you know that in the previous topic, what we discussed is that this diagram, that from an external point you are drawing two tangents to the this hyperbola. Okay. And it touches the hyperbola at two distinct points, A and B. Now, the straight line AB is called the chord of contact. So, how we can draw the straight line AB? So, let us draw the straight line AB in blue color. So if we draw the straight line AB, it will be something like this. Correct, dear students? So this line, what you see the blue in blue color, that is known as the chord of contact. Okay. So what I'm saying is that this is known as the chord of contact. Okay, dear students. So now, what is that equation of that straight line AB? So equation of that straight line AB is t equal to 0, where t is the value of the expression x(x1) by a square minus y(y1) by b square minus 1. Okay. So here t also a symbolic representation. There is no question with the it is the equation of the tangent. Okay, it is the equation of the chord of contact, but to remember it, this is a symbolic representation, t equal to 0, because we know t stands for tangent, and that is the value of the expression x(x1) by a square minus y(y1) by b square minus 1. I have said this thing many times, for ellipse as well and for hyperbola as well, so that you should not get confused. Now, the next point, dear students, is, we are going to find the equation of chord in terms of the middle point. So let me first explain you what is meant by that, the middle point. So let me take you to the next page and explain you further. So to explain in a more effective manner, the best, best is to, give you a diagram, and then let me explain from there. So in view of this, please consider this diagram as you see in front of the screen, dear students. Okay. Let me first place it, then let me discuss. As you see in this diagram, that AB is a chord. Okay, AB is a chord. So this is one point, and this is another point. Now, what we know what is the the midpoint of this of this chord. That is the aim. The point aim is nothing but the middle point of the line segment AB. So what we know, we have two information at our hand, dear students. The first information is the equation of the hyperbola, which is the standard equation x square by a square minus y square by b square equal to 1. That is the equation of the hyperbola. Okay, is that x square by a square minus y square by b square equal to 1. That is the equation of the hyperbola. Now, that equation of the hyperbola, this is the first information we have. And the second information what we have is the midpoint, the coordinates of the midpoint M, having coordinates x1, y1. Okay, midpoints of the line segment AB. Let me clarify once more, dear students, in case I made any mistake in my slip of tongue. AB is a chord. That line segment is the chord. Now, what we have the midpoint of AB. Okay, that is the point M. That coordinates we are aware of, that is x1, y1. That is the second information. And the first information, we know the equation of the hyperbola under consideration. That is x square by a square minus y square by b square equal to 1. With these two information, we are going to find the equation of the line AB, how we can find that one, and it is exactly like what we discussed in case of ellipse, and here it is, I'm going to just mention. So dear students, so my statement will follow here, and let's take. Let the pair of tangents from an external point, let the pair of tangents from an external point P to the hyperbola, okay, um, you know, x square by s square minus y square by b square equal to 1 touches the hyperbola at two distinct points A and B. And we know the coordinates of the middle point of AB, which is x1, y1. Now the straight line AB is called the chord of contact, and its equation is T is equal to S1. Okay, so what is T, dear students? T is the value of the expression x1 by a square minus y1 by b square minus 1. And what is S1? S1 is x1 square by a square minus y1 square by b square minus 1. That is S1. So T equal to S1 is the equation of the chord of contact in terms of the middle point. I hope it is absolutely clear. And we move to the next point, and that is a quite a new point as long as the conic section is concerned, because it is not there for the other two conics, parabola and an ellipse, that is called the rectangular hyperbola. Okay, so let us first understand what is meant by a rectangular hyperbola. Okay, so a hyperbola whose asymptotes are at right angle to each other is called a rectangular hyperbola. Dear students, in the previous session, we discussed in details about the asymptotes and the asymptotes of a hyperbola. Okay, you can look back to my previous lecture on asymptotes. Asymptotes is nothing but a tangent to a curve at infinite. Okay, if I can tell you in brief what is for asymptotes. For example, that you have a curve something like this. This is a curve. Let me draw the curve something like this. A curve y equal to fx. Now, dear students, we have a straight line. Asymptotes is nothing but a straight line, first of all. That you need to make sure that asymptotes is nothing but a straight line. And I am going to draw a blue line, such that it is not touching that curve at any finite point, and we say it is going to touch that curve at infinite. This is one way of looking into it. And another way of looking into it is that asymptotes is a straight line such that the distance between that straight line and the curve is approaching to zero as both are proceed towards infinite. Okay, both the statements are true, whatever I said. So that is called asymptotes. Now, in context to hyperbola, what are asymptotes? So I can give you diagram from our previous session to understand that how asymptote looks like for a hyperbola. Okay, dear students, so let me show you that that how it looks like in context to our discussion of hyperbola, that asymptotes. If you look into this straight lines, dear students, equation of the hyperbola is x square by a square minus y square by b square equal to 1. And if you see, there are two straight lines. One straight line is this one, and the other straight line is this one. These two are asymptotes. That means these two are the lines, touching that, hyperbola at infinite. Okay, so that is why they are called asymptotes. Now, what is rectangular hyperbola? A rectangular hyperbola a hyperbola whose asymptotes are at right angle to each other is called a rectangular hyperbola. Okay, so a hyperbola whose asymptotes are at right angle to each other is called a rectangular hyperbola. Now we are going to derive, uh, you know, uh, the further from that. So from the discussion of asymptotes, dear students, we know the angle between the asymptotes of the hyperbola x square by a square minus y square by b square equal to 1 is equal to 2 tan inverse b by a. Dear students, you can find it from here also in the diagram what you see. Okay. In the diagram what you see, dear students, there are two straight lines, that one is y is equal to b by a into x, and the other one is that y is equal to minus b by a into x. If you look into these two, that asymptotes equation and find the angle between them, you will find the angle between them as 2 tan inverse b by a. You know what is the angle between the two straight lines having the slopes m1 and m2? It is tan inverse of m1 minus m2 by 1 plus m1 m2. Correct? No? So that if theta is acute, then you take the mod value of that. So dear students, so what I'm saying is that the angle between them is 2 tan inverse b by a. Now the hyperbola x square by a square minus y square by b square equal to 1 will be a rectangular hyperbola if and only if the angle between them is 90 degree. That means we can say that 2 tan inverse b by a should be equal to pi by 2. That means tan inverse of b by a should be equal to pi by 4. So 2 tan inverse b by a is equal to pi by 2 is the necessary condition for rectangular hyperbola, because the angle between its two asymptotes is 90 degree. So that means tan inverse of b by a is equal to pi by 4. Okay, that means b by a is equal to tan pi by 4. Eventually we get b by a is equal to 1, because we know the value of tan pi by 4 is 1, and we get b is equal to a. The moment we get b is equal to a, we get b square equal to a square. And b square is what? In case of hyperbola, the relationship between b, a and e is that b square is nothing but a square into e square minus 1. So we get a square into e square minus 1 is equal to a square. Hence we get e square minus 1 is equal to 1, since a square is not equal to 0. And eventually we get e is equal to root 2. E square is equal to 2, it means e is equal to plus minus root 2, but e cannot be negative. Why? Because if you go back to the fundamental definition of E, eccentricity, it is a ratio of two distances. A ratio of the two distances cannot be negative. Hence, we took that E is equal to root 2. I hope it is clear, dear students. Now, as it is clear, now we proceed further that, so we get one very important point. The value of E is equal to root 2 in case of a rectangular hyperbola. Now, dear students, so I'm going to discuss some relevant points here. The first point, what I'm going to say is that, the equation of the rectangular hyperbola, refer to its transverse and conjugate axis as coordinate axis is equal to x square minus y square equal to a square. So, what is meant by that? Let me explain you a little bit. Is that if you recall, from the fundamentals attributes of a hyperbola, it has transverse axis and conjugate axis. Now, if we consider the transverse axis and conjugate axis at the coordinate axis, okay, then that means x-axis and y-axis, then the equation of that rectangular hyperbola is becoming x square minus y square is equal to a square. That is the first point. Now, the next point, what we are going to discuss is something like this. The equation of the rectangular hyperbola whose asymptotes as coordinate axis. The equation of the rectangular hyperbola whose asymptotes, are the coordinate axis, is is xy is equal to c square. Let me explain you. Let me first keep the statement in front of you, and then let me explain you, dear students. So what I wanted to mean is that the equation of the rectangular hyperbola with asymptotes at the coordinate axis is xy is equal to c square. Okay. The equation of the rectangular hyperbola with asymptotes as coordinate axis is xy is equal to c square, where c is equal to a square by 2. Okay. Now, the for a rectangular hyperbola, that is xy is equal to c square, okay, the coordinates of any point on the curve is, you can write that is ct and c by t. Okay. Where t is a parameter. So where t is a parameter, and I will explain you the significance of t here. So before that, let me place the statement from the study material here, and then we can discuss further. So what I wanted to mean, just give me a second. So let me place it here properly. Let me place this point, dear students. Actually, I was, making it in a proper format so that you get it properly. Yeah. So what I wanted to mean is that for the rectangular hyperbola xy is equal to c square, the coordinates of any point on the curve is taken as ct, c by t, where t is a parameter. The significance of t is, that minus 1 by t square represent the slope of the tangent at the point ct, c by t. That you can experiment, dear students. Okay. And we already discussed about application of derivatives few points, and there if you see the tangent normal from a differential calculus point of view, because dy dx represent the slope of the tangent at the point xy. From there also you can derive this, and you get you will understand that y and the minus 1 by t square is actually represents the slope of the tangent at the point ct, c by t. Now, dear students, that we are going to discuss about the equation of tangent to the rectangular hyperbola xy equal to c square at two different points. The first point is that we all are aware of that Cartesian coordinate system x1, y1, and the other point what we are going to discuss is that the parametric point, that is we just discussed about the parametric point is ct, c by t, and we are going to discuss that point. Okay, so let me place the statement in front of you, and then we will discuss further. Okay, so the equation of tangent to the rectangular hyperbola xy equal to c square at the point p x1, y1, at the point p x1, y1 is xy1 plus yx1 is equal to 2c square. That is the first one. That the equation of the tangent to the rectangular hyperbola xy is equal to c square at the point x1 comma y1 is xy1 plus yx1 is equal to 2c square, and at the point p ct comma c by t is x by t plus ty is equal to 2c. Dear students, you can all derive it, and also you can after derivation you can actually remember it also, because remembering is more preferable. And the next point what we are going to discuss is that the equation of normal to the rectangular hyperbola. So we discuss about the tangent, dear students. Now what we are going to discuss about the normal. Okay, and I'm going to place the statement in front of you. Okay, and the equation of the rectangular hyperbola, equation of normal to the rectangular hyperbola at the point xy at the equation of the rectangular hyperbola is xy is equal to c square, and on that hyperbola at the point ct comma c by t, the equation of the normal to the rectangular hyperbola xy equal to c square at the point ct comma c by t is xt cube minus ty minus ct power 4 plus c is equal to 0. So this is the equation of normal, and with this, dear students, I conclude the class on hyperbola. So these are the all these in today's session and the previous two sessions we discussed the fundamental points of hyperbola, and the advanced point we'll discuss later once we are done with good amount of practice. So with this note, I would like to conclude the class here, dear students, unless you have any specific question for me. Thank you very much.